Okay, good morning everyone and welcome to the November Soils Network of Knowledge webinar. I will now introduce Ashley Webb, who is Leader Soils North with DPI Agriculture. And Ashley is a Senior Research Scientist in Soil and Water Management and an adjunct at the University of New England. Prior to joining DPI in 2013, he was employed for 12 years by Forests New South Wales in a range of roles relating to sustainable forest, soil and water management. Ashley has published over 40 refereed papers and 30 industry reports relating to catchment processes and the effect of best management practices on water quality and the aquatic environment. Today, Ashley is going to explain cost-effective road and track management options to maximise soil and water protection techniques that focus on reducing erosion and therefore the delivery of sediment to waterways.
Good morning. Yes, excellent. Okay, well, thank you for that introduction, Abby. As explained, I'm going to give you a bit of a rundown today on road and track management for soil and water protection. And it's really an introduction to this topic. There's a whole lot more that could be covered, but I will walk you through some of the concepts and recent research, and then hopefully in the end point you to some further resources. So without further ado, the outline of the talk that I'd like to give today is basically I'll run you through some terminology around roads and tracks and some of the structures that I'd like to talk about because that might be new to some of you. I will talk to you about, excuse me, what are the main sediment sources from roads and tracks in different environments, and probably importantly go through some erosion control measures, and finally talk about reducing road to stream connectivity, and that's around reducing impacts on waterways in the aquatic environment. The photograph on the right there is in a national park on a walking track, and I guess I wanted to point out that whilst most of the work that I've done in this area has been in forestry sort of environments, the concepts are applicable across land tenures. So it doesn't really matter whether a track is in a national park, in a state forest, on Crown land, on a travelling stock route, on private land. They all act the same way, and all of these concepts that I'll talk about are applicable in those environments. So, moving on to terminology, the main there's two types of roads that I really want to talk about today. The first one being ridgetop roads, and you'll often see these with what we call mitre drains. I'll show one of those a bit later on either side of the road. These today are what we recommend as the, if you're going to build new roads, try and locate them on ridge tops because that keeps them well away from waterways. They're usually of lower slope, and for reasons that I'll explain later, they're probably the most desirable in the landscape. The other type of, or main type of road, if that slide's now come up for you, is a side cut road. So these are ones that basically are cut into the hill slope, and you can see on the right hand side of the screen there we'll have often a large cut batter and a table drain, and the actual road surface itself will generally drain towards that table drain and the cut batter, and that creates some issues for where water goes and how it's managed. So if we look at, in the next slide, a schematic diagram of what the drainage on these road types generally looks like. On a ridgetop road, which is the one on the left-hand side, we generally have that dotted line down the middle is what we call the crown. So water is drained from either side of that crown to generally a table drain on either side, and water is then removed from the road via things called mitre drains, which I'll show a photograph of soon. On the right-hand side, on a side cut road, as I mentioned, generally the road will slope towards the cut batter, which is on the left-hand side in this diagram, to the table drain. We call that crossfall drainage, and in this case it's infall. You can have a situation where water flows to the outside of the road called outfall drainage, and I'll show a photograph of that in a minute. What happens is the water flows in this instance from the right to the left into the table drain, and then somehow has to be removed from that table drain. So we would have generally what we call a sump, which then is connected to a pipe called a relief pipe that goes beneath the road and discharges the water out onto the fill batter, which is on, in this case, the right-hand side of the road. Looking at that in cross-section, on the next slide, you can see, as I mentioned, quite often there will be there's a hill slope above the road. This is a side cut road, just showing you that the water on the surface of that road will flow typically towards the table drain, into that sump, through the relief pipe and out onto the hill slope below the road. Excuse me. In reality, looking at the next slide, which has just popped up, is often a combination of infall, outfall, table drains, miter drains, you name it. So in this situation, in this particular photograph, you'll see there's a cut batter on the left-hand side, a fill batter on the right-hand side, and the upper part of the road here, there's infall drainage where the water is flowing towards the table drain, but on the lower part of the road here, there's actually outfall drainage, so the water is going towards the outside of the road surface. Typically, in terms of a water quality scenario, it's best to have outfall drainage. It's easy to get the water off the road. You're less likely to create situations where you'll promote gullies or rill erosion. However, there are certain situations where that's unsafe, so it's not always practiced. Moving on to the second part of the talk, I wanted to highlight how important roads are in the landscape as sources of sediment and why this issue of draining them properly is important. So this is some work that was done here by the CRC for Catchment Hydrology, which ran for a number of years and did a lot of work in particularly forest environments. But what cesium tracer experiments and also rainfall simulator studies showed over a number of years is that roads are, particularly in forested catchments, the main sources of sediment. So you can see here that they are at least an order of magnitude more important in terms of the contribution to sediment concentrations that they make relative to, say, snig tracks or what you might call skid trails and the general sort of harvest area. So that's why we focus a lot of our effort on making sure that they're managed properly to reduce the likelihood of impacts on waterways. Some other work, moving on to the next slide, has shown the effect of traffic intensity. I mean, this is common sense, but you know, some numbers have been put around these things to show that obviously the more a road is used and the heavier the traffic that uses that road, the more sediment is generated from that particular road surface. So a heavily used road, in this case, which may be used for hauling logs or, you know, carrying B-doubles and large trucks, is going to generate more sediment than a temporarily used road, and certainly more than an abandoned road in most cases. Some other work that's been done on sediment generation, this is from Victoria. So Gary Sheridan and Phil Noski from the University of Melbourne did a lot of really good work. On the left-hand side there, you can see a tipping bucket setup that they had. At the top of that tipping bucket, you can see an open pipe that basically runs water from a drain into the tipping bucket. So they were able to calculate how much water and how much sediment came off of different road surfaces, and they then converted this in different rainfall situations and on different road slopes into some useful nomograms that can identify how much sediment will be generated from different road types. It's, again, common sense. I mean, the higher the rainfall erosivity, the greater the slope, the more likely you are to get erosion of the road surface and therefore generate more sediment that then we have to deal with in the landscape. So, the principles of erosion control. Effectively, drainage spacings are what we use mostly to reduce erosion of the road surface and the table drains. This has been the case for a number of years. So this particular figure here shows the recommended, it's actually for the north coast of New South Wales, maximum drain spacing for a given road or track slope. So as you can see, when you have a very low slope, you know, drains could be spaced up to 250 metres, but as you get into the steeper scenarios, particularly here, if you had a track on a very steep 30-degree slope, you're looking at a pretty low spacing between drains to ensure that you don't create erosion of the surface of the track or the road. Just a quick note there that most roads are not recommended to exceed 15 degrees, so the higher slopes there refer more or less to tracks. So just looking at that, in the next slide, in terms of some tables, again, these are from the Upper Northeast Environment Protection Licence issued to what's now the Forestry Corporation of New South Wales. You can see there, as I mentioned, a road grade in degrees of just 1 degree can have a maximum drainage distance of 250 metres, whereas if you get down to, at the bottom, a 30-degree slope, with a track, it's recommended that you don't have drains spaced any further apart than 15 metres. So again, common sense, but some useful guidelines. Just to show you what some of these things look like, in the next slide, this here is a, maybe not the best photograph, but shows a mitre drain on a ridgetop road. So you'll often see these basically on the sides of the roads. There'll be a small table drain to the side here, another one there, and you'll have mitre drains quite often alternately placed along the road on the edge. I call them mitre drains. Sometimes you may see them referred to in the literature as push-out drains. I think that might be an American term. Another common type of drain that's used in the next slide is a rollover drain. I'm sure all of you have driven down a steep track in a four-wheel drive and come across these. Usually used on steeper roads and those that are not used that often by heavy traffic, because as you can imagine, a rollover that can be fairly high, it can be difficult for trucks and so on to pass over, but certainly they're a very effective method on steep tracks of draining the road surface. In the next slide, another type of drain that's popped up now for you is a crossbank. These are typically used effectively on temporary tracks, those that have been closed. In this case, it's a SNIG track or a skid trail that's been used for forest harvesting, and they're a very effective method of temporarily, between the use of that road and the next time that will track and the next time it needs to be used, they're a very effective method of draining that road to prevent erosion of its surface. In this case, it's a natural surface. One thing to be wary of if these are being constructed is not to disturb the subsoil, particularly if you're in a duplex soil. I've seen this in a number of cases. If that subsoil material is disturbed and then mounted up onto the crossbank, it can create some issues for erosion of that surface. I mentioned that rollover drains are not always desirable, particularly in this case in a forestry scenario in a haulage situation. So there are other options available, and quite often you'll see these in state forest roads, such as this, a rubber flap. So this is effectively just a piece of conveyor belt that's been cut up and buried within the surface, but it forms the same, it fulfills the same purpose. So basically, it's a temporary structure that water flows down the road, hits the flap, and is diverted off into undisturbed filter strip. The advantage of these for trucks is that basically they will obviously lie down when the truck drives over it and then stand up again. So they're obviously not a permanent solution because they do wear out over time, but certainly when the road is needed to be used by a heavy vehicle, frequently they're a good option. Other things you might see in these scenarios are what we call a spoon drain or a C-channel, and they again have their advantages and disadvantages. Another thing to point out here in this slide is that you can see the rubber flap here, and there's one up on the other side of the bridge. This is a stream crossing, and these are very sensitive, which I'll get onto in a minute, for creating issues for water quality. So it's very important that roads are drained either side of crossings, and we typically recommend that you do that between 5 and 30 metres away from the crossing on either side. I mentioned when we have that infall situation with a cut batter and a table drain, that you then have a need to remove that water from the table drain away from the road. So in this situation, you can see the water here in the table drain is flowing towards the bottom of the screen. It flows into what we call the sump. These old, well, I call them old, square right angle types you find typically on older roads. I'd say in this case, I think it was built in the 50s or 60s. And they are then connected to a relief pipe, which is obviously a pipe which runs underneath the road surface and discharges the water on the hill slope on the bottom side. More recently, in typically, I know councils use these, and also the forestry organisations, they use more curved sorts of sumps in their table drains. The advantage of these is that rather than having a right angle, they have a curved shape beneath the surface, which helps with self-cleaning. One of the major issues with managing table drains and sumps is obviously that they block up with debris and sediment, so something that's self-cleaning is obviously better for maintenance, and then make sure that it's more effective in the long term. So just following up on that point, design and maintenance are really important. So in this particular scenario, you can see there is a lot of water running down the table drain here on the right-hand side of the photograph into the sump, and then obviously into the relief pipe and out under the road. But maintenance is really important. So you can see in this scenario on the left-hand side of the crown, this is the crown down the middle, the water is actually running down the road surface. So that in itself can create an issue because that maximum drain spacing that I talked about will be exceeded. And over time, if this isn't rectified by regrading the road surface and making sure the drainage is correct, then you can end up with rills and or gullies on the road surface, and that in itself becomes a nightmare for soil erosion and water quality control. One thing, a little tip here is that these roads obviously look very different when they're wet compared to when they're dry. So the best time obviously to go and inspect your drainage is during a rainstorm. So that's typically what I would do, would be to go out when it was raining and see which way the water was running. And that's something I'd recommend that you do. Another consideration might be it's really important to make sure that the relief pipe that has enough to convey the road runoff. So quite often you'll find in an intense rainstorm, if the relief pipe isn't large enough, the water will either back up behind it and sometimes overtop it, which then creates that issue of the maximum flow distance that's recommended being exceeded, which creates problems of erosion below the drain on the road surface or in the table drain, which in many scenarios I've seen those eroded down to bedrock. Another thing to make sure is that these particular structures are cleaned regularly and maintained, because they can, as I mentioned, particularly those right angle ones, block up with sediment or debris, and then they effectively become useless. So that again is something that needs to be kept in mind. There's lots of tips that I could provide. I'll just mention a few more here. It's also important to follow the design principles of these different drainage structures. In this particular case, the rollover drain itself is effective, but the outlet on it is far too steep. So you can see to the right of that hard hat, or to the upper right of that hard hat, there's erosion occurring in the actual outlet of the rollover bank itself, which is something that should be avoided in terms of preventing erosion and water pollution. Another thing, not picking on motorbike riders, but it's a maintenance issue, is that these things need to be constantly checked and maintained, because whilst you can have a really effective and even large rollover bank, it only takes a bit of wet weather and some motorbikes or mountain bikes or anybody to breach the top of that cross bank or rollover drain, and it becomes ineffective. So again, it's a maintenance issue. These things need to be checked fairly regularly to make sure that they're not being exceeded, because in this particular case, if it's a steep track, that that indentation there is basically a breach in the top of the bank and can create, you know, an issue where water will overtop the bank and then erode further down the hill slope. So, moving on then, I guess in terms of reducing effects on water quality in the aquatic environment, aside from minimising erosion of the road surface as much as possible, the whole principle here of reducing effects on water quality is to ensure that road to stream connectivity is minimised. So if you can look at the top right there, this is probably the worst case scenario, and it's a photograph from the 70s actually, but you can see that roads in some particular environments dominate the landscape, and what we want to avoid is erosion of those surfaces and connectivity with drainage features. So how do we make sure that this doesn't happen is a rather important question. So moving on, if we consider, we've talked about soil erosion and its generation, one of the principal questions here is, what is the destination of road runoff? So what are the different ways that runoff and sediment from a road can enter a stream? Well, there's a few different possible outcomes here. So the road runoff, this is probably the best outcome, is that if water is diverted onto the right surface, it infiltrates into the soil below a road drainage outlet. That creates for us no real problem for water quality. So that's probably your best outcome. What can happen is that water could also be discharged into a small gully, say, that might have formed below a pipe or a drain outlet. But if that then doesn't extend to a stream channel, that in itself is not a major problem. So again, a reasonably good outcome. The third way that road runoff can enter a stream is via a stream crossing. I showed that photograph earlier with the rubber flaps on either side. It's pretty much acknowledged that, you know, that section of road between those drainage features, those drains and the stream itself is going to create a problem. So it's acknowledged that there is a small section of road there that is going to be contributing sediment and runoff directly to the stream. That is largely unavoidable, but needs to be managed as well. Looking at a worst case scenario, is that you can have a gully form below a drainage outlet that then indirectly links the road with the stream. That is not a great outcome because effectively you are extending the stream network up to the road. So that's not a great outcome. The fifth way that road runoff can enter a stream is below an ungullied slope, and this is via overland flow from a drainage outlet. Again, not the best outcome. So I'm going to run you through some photographs of these different destinations of road runoff and then talk about how we may manage those different outcomes. So, looking at this in a photographic and conceptual sense, if we look at the top two photographs, those are the direct linkages I was talking about, where at a stream crossing, basically runoff and sediment, or dirty water if you like, can directly enter a stream or a waterway. So that's undesirable, but not always avoidable. So it's acknowledged that there are some sections of road that are going to be contributing some sediment to the waterway, but that needs to be minimised. One thing that can be done to reduce that, as I mentioned, is that 5 and 30 metre away from the crossing drainage. But another thing that quite often can be done is you could armour the surface of the road with gravel or something like that, which can reduce the amount of sediment that it generates. Looking at the diagram and the photographs at the bottom, the channelized connectivity that I mentioned is represented by this diagram here. So where you have a relief pipe, so you've had the water flow into the table drain, into the relief pipe, under the road, it then can create a gully below that relief pipe outlet. I'll get on and talk about why that might happen in a minute. But then if that creates a gully, which is pictured on the bottom right, that extends to the stream network, you're effectively providing a conduit for the dirty sediment-laden water, sediment and nutrient-laden water, to go from the road directly into the stream. Not a great outcome. On the bottom left is a photograph of what we'd call a diffuse pathway into a stream. So in this case, there's an outlet, could be a miter drain or a relief pipe, that water is discharged out onto the hill slope, but it is such that it's of a volume and at a rate that is greater than the capacity of the hill slope to infiltrate, and so there is this overland flow that then can reach the stream as well. Not probably as bad as the channelized connectivity, but again, it is still connectivity that has the potential to deliver sediment-laden water from the road surface into the stream. So just to picture the channelized and the non-channelized options here. On the left-hand side, this is below a relief pipe. You can see that a gully, this is right beneath where obviously my feet were here, a gully has been created at the outlet of the pipe that has taken water from the road, and that gully extends all the way to this stream. That's the head of the first order stream in there. So basically what we've done is we've effectively extended the stream network all the way up here to the road. So it provides, let me go back up, provides a direct connection between the road and the stream. That's a really poor outcome in terms of water quality for the pollution of the aquatic environment. As opposed to on the right-hand side, where we have a non-channelized outlet of a pipe, you can see there's greater potential here for the sediment-laden water to infiltrate into the topsoil and therefore drop the sediment that it's carrying and not create a problem down slope for the aquatic environment. So that's a more desirable outcome than the option on the left. Moving on, there is a bit of science around this, so it's pretty well acknowledged that the creation of gullies or gully heads is related to a slope area threshold. This here is some work that Jackie Croak and Simon Mockler did on the south coast of New South Wales that came up with a relationship between the contributing area, which is effectively the catchment area above a pipe or a drain, and the slope of the receiving hill slope. So as you can see, if you're above that line, there's a lot of channelized outlets, and if you're below that line, the majority of the unchannelized outlets are depicted there. So basically what we aim to do is make sure that our contributing area, or if you like a proxy for the road or drain spacing above the outlet of a drain, is not above that threshold. Therefore we reduce the likelihood of creating a gully and that channelized connectivity with a stream. This work reflects also a lot of the work in this area that's been done in the Pacific Northwest in the US, which came up with similar thresholds. But again, it's acknowledged that there's a slope area threshold. So I've also looked at this issue on the north coast of New South Wales with a colleague, Ian Hansen, who worked with me and then went to Crown Lands, and we looked at something like 150 drains across a variety of land tenures, national parks, Crown Lands, state forests in northern New South Wales, around the Coffs Harbour, Bellingen, Woolgoolga kind of area. And one thing that's really important to note here is I talked earlier about the erosion of the road surface being related to the slope of the road. And that's what we always used to think about when we drained roads, is we were only worried about erosion of the road surface and the generation of sediment. But what you can see is, in the majority of situations, the road is naturally a lot less in grade than the hill slope that is receiving the water where the drains discharge onto. So that's something we need to keep in mind. You know, we may have a very gentle grade in a road, which means that, you know, under the former guidelines I talked about, it would be possible to space the drains a long way apart, but then you create the issue that you're then if you're discharging water onto steeper slopes, you know, they can be 30, 40, even up to 50 degrees in some places, then that water has the potential to create a gully that then directly connects that road. Typically this happens in side cut scenarios, you know, that connects that road between, connects that drainage outlet with a stream and creates a problem. So what did we find? Well, actually we found that the threshold that Jackie Croak came up with on the south coast actually applied on the north coast if we looked at the total contributing area when we calculated in our calculations. And what I mean by that is the total contributing area being not only the area of the road surface above the drain contributing water, but also the area of the table drain and the cut batter above it. So in some scenarios, you could imagine on a very steep slope, say 40-degree slope, the cut batter can be a lot greater in area than the road surface itself. So what do we find? Actually, that threshold, if we included the total contributing area above the road drain, was 100% accurate in predicting whether gully drain outlets would be gullied or not. So these are the darkened squares and circles. So a square there, SRP meaning a sump with a relief pipe, and ERP being an elbow. That's the curved relief pipe, sump and relief pipe. What you see, the difference between the work that I sort of did and what Jackie Croak found on the south coast was that whilst we could predict where the channels would be created at drain outlets, there's a whole lot of other drain outlets that are above the threshold that aren't gullied. And there are reasons for that I won't have time to go into here. But in any case, I think it's still a very useful guideline to be able to make sure that we stick below that threshold. So the other way, as I mentioned, that water can be delivered to streams is via a diffuse pathway, and a model that we found to be quite useful was developed by Peter Hairsign from CSIRO some time ago when he was part of the CRC for catchment hydrology, and it's called the VBT5 or volume to breakthrough model. So what it does is predict the probability of runoff reaching a stream through that diverse overland flow that I talked about. And the way it operates is it basically says to you how much water, what volume of water can we put on a 5-metre segment of a hill slope that hill slope is capable of infiltrating. So, how much water can we put on before overland flow is created? And then that model is applied downslope so that you can work out the probability under a given rainfall scenario and for a given road segment, how much water is likely to, what's the probability of that runoff being delivered to a stream via an overland flow path. So how does that operate? So again, going back to that work I did on the north coast with Ian, this is probably a bit of a confused diagram for you to look at, but what you can see is for each of the drains that we looked at, we were able to plot what we were able to calculate, what was the flow path and the distance to a stream. So this is the x-axis. So you can see some roads are located close to streams, so they can be less than 50 metres away, right up to nearly 1,200 metres. So those are obviously ridgetop roads. And by having calculated the total contributing area, which is the road surface plus the cut batters and the table drain above each drain, we then apply the VBT5 model for different 30-minute duration rainfall events, so for a 1-year event, a 2-year event, all the way up to a 100-year event, and we were able, using a GIS platform, we were able to calculate for each of those drains what was the likelihood that they would be connected to a stream via diffuse overland flow under those scenarios. So as you can see in the roads we surveyed, during a 1-year rainfall event, 20% of the drains were connected to a stream, whereas if you move right up to a 1 and 100-year event, up to 83%. So, during those really intense storms, it's pretty well acknowledged that the majority of drains are actually going to be connected to the stream network. Again, which highlights why all the previous research has shown that roads are the greatest contributors of sediment to pollution of waterways, particularly in these environments. So, putting all that together, I was a part of an ARC linkage project a few years ago that had a number of research and industry partners, including ANU. So the ICAM modelling group basically ran the overall project with University of Melbourne. So the Forestry Corporation of New South Wales, what was the Department of Sustainability and Environment in Victoria was involved, the MDBA, the Southern Rivers, what was CMA, Eurobodalla Shire Council, OEH in New South Wales, and also the ACT government. And we came up with a framework or a decision support system, which is called RoadCap. I'll give you the link to that. You can look it up, which basically applies all of these concepts that I've talked about for road drainage in the landscape in a GIS platform to work out where's the best location for your roads and also the drains. So the inputs to it are obviously a high resolution DEM. The higher the resolution, the better. If it's LiDAR, that's great. If not, use the best you've got. A stream layer, again, probably best if it's been LiDAR derived. You need a road layer to see where your roads are, or of course if you're going to build roads, then it's possible to put in possible locations for those. The GIS itself can calculate what the gradients are of the roads and also the hill slopes. We can work out the distances to the streams. Applied that gully threshold that I told you about from Croke and Mockler's work, also the VBT5 model. Overlaid on all of this, of course, is that original guideline of what are the best drain spacings to reduce erosion of the road surface itself. But effectively, putting all of that together, we can come up with some risk maps across the landscape that show us where are the best places to locate roads and where should the drains be placed. So just an example output of that, this is a GIS layer showing the maximum drain spacing across the landscape here in a forest compartment to prevent gully erosion. So you can see the blue areas are obviously where you're less likely to get gullies created at a drain outlet, right down to the red ones, which are obviously going to be steep hill slopes and so on, where it's highly likely that you will get a gully form at a drain outlet. And what this does is provide us with, if you're going to have a road in any of these places, it tells us what is the maximum road contributing area that you should have above a given drain to prevent that gully from forming. Similarly, you can see here an output layer regarding diffuse delivery to streams. So no surprise that the further away from a stream you are, the greater the road contributing area can be above a given drain outlet. So in this case, the blue areas show you where it's probably better to locate roads, which unsurprisingly are along the ridge tops. And as I mentioned, the closer you get to streams, you can see the stream network here in the redder colour. Obviously, you're going to need your drains a lot closer together because there's a high potential for that delivery, diffuse delivery of sediment and water via overland flow. And then putting all of that together, you can come up with a final risk assessment map, which again shows you where are the best places to either locate roads, or if you've got an existing road network, you can utilise this tool or decision support system to tell you what are going to be your problem drains, and then work out which ones you may need to relocate, if you need to add new drains, or if it's best even, in some cases, this has been applied to show where it's the best outcome for water quality might actually be to decommission a road and build one in a different location. So that is a useful tool. So I might leave it there, but some resources that you could refer to if you wanted more information, apart from contacting me, is there's a link there to that RoadCap model. So go to the Fenner School at ANU's website and look under their research products, and you can download, if you've got ArcGIS, you can download that that DSS and apply it. There's a great resource produced by New South Wales DPI called Saving Soil, and in that there is a chapter on road and track management. I've put in there a photograph of the Forest Soil and Water Protection Manual. It's from what was State Forest of New South Wales. If you Google that on Forestry Corporation of New South Wales, you can find it. It's getting a little bit old now, but it's actually really good. So I know the National Park Service still use it, as do the forestry people, because it's got some wonderful tips and guidelines in it. More recently, the Queensland government produced some soil conservation guidelines which are up to date and have some wonderful tools and tips as well, so that's also a wonderful resource. And I'll hand back to you, Abby. Thanks for your attention, everybody.
Thank you very much, Ashley, and a special thanks to Ashley, because Ashley's actually been away overseas until I think the day before yesterday, so he's had to overcome jet lag and things like that to present today, so thank you very much. There is now the opportunity to ask a question of Ashley or to have a comment on what Ashley said, so if anyone would like to do that, now's your opportunity. Steve Kimber has a question.
Thank you, Ashley. You alluded to the problem of traffic on tracks. Do you have guidelines for the control of traffic movements in conditions that are less than perfect? I'm guessing that a lot of the damage to the roads is when they are wet and you're getting traffic on them.
Yeah, definitely, Steve. So thanks for the question. Yeah, look, it's obviously not recommended that roads are used when they're wet, particularly gravel roads or natural surface roads, and indeed, if you're obviously a logging contractor or whatever, there are restrictions in New South Wales that say that if there's been a certain amount of rainfall and the road surface is saturated, then all haulage has to stop. So, you know, there's no use of log landings or haulage roads when it's wet. So yeah, absolutely.
Thank you, Steve.
But of course, you know, yep. Oh, I was just going to say, you know, that's obviously what occurs in the situation where activities are regulated, but, you know, most of us realise that people who recreationally use tracks for four-wheel driving or motorbiking or whatever actually like to be out there when it's wet, so that's a challenge to manage.
I just had I guess a point of clarification. You talked about infall or outfall roads and mentioned that outfall roads were the better way of shedding water from the road, but in certain circumstances they weren't appropriate. And I just wanted to clarify that often on steep slopes is where they're not appropriate because it's dangerous for them to be built and to be transported on. Is that correct?
Exactly, Abby. Yeah, that's what I was getting at.
Yeah.
Yeah, so I mean, I'm not an engineer, but there are certainly those considerations to take on board. So, you know, typically you'd find a road would camber away from the on a bend away from the outside so that it is more safe. So whilst from a drainage perspective it's ideal to shed water as quickly as possible via outfall, there are some situations like those steep slopes you mentioned where it's not appropriate. Yeah.
Yep. Okay. Thank you. And Luke, did you have a question?
Yeah, thanks, Abby. Just wanted to ask Ashley, are there any other practical tips for reducing erosion at drain outlets?
Yeah, thanks, Luke. I did kind of allude to that. There are reasons why sometimes, despite those thresholds, there isn't erosion at a gully outlet and, at a drain outlet. And one of those reasons is that it's recommended that certain other best management practices or soil conservation measures are put in place. So one of those might be a thing called a drop-down flume, which can be installed below the drain outlet, or a rock dissipator. It's also important to have, you know, a proper head wall around the drain. Make sure the fill batters are consolidated properly. There's all sorts of things like that that can be done to reduce the potential for erosion at a drain outlet. And then, look, in some cases, even temporarily, things like hay bales can be used, jute meshing, you name it. So there are reasons why in that slide that I showed there were some drain outlets above that threshold that weren't gullied. So yeah, definitely there are some things that can be done.
And it would be important to have a look at having those designed correctly so that they are
Absolutely.
at the correct capacity for the volume of water.
Absolutely. Definitely, Abby. Yeah, and they will. You know, if you look up some of those manuals that are on the screen there, there will be some good guidelines around how and when to put those structures in.
Okay, thank you. We have another question here from Johanna Kempf. And Johanna said, Ashley, have you taken into consideration vegetation cover and soil regolith, as these would influence how much sediment would reach the creek?
Yep. Definitely. So, interestingly, for both the gully threshold and also the volume to breakthrough model, there's not a great difference with different soil types, certainly, and regolith tends to be a fairly constant output of that model, but vegetation cover does make a difference. So I've applied this here in a forest environment sense, because that's obviously where I ran those models, but some of the work that came out of the Victorian government and also the ACT area after the wildfires around Canberra showed that there were some major changes in the hill slope hydrology following those wildfires. So you create hydrophobic soils, you remove the surface vegetation and so on, and obviously these models don't necessarily apply for a period of time. So yes, that vegetation cover can play a major role. Yep. That makes sense?
It does indeed.
Certainly in New South Wales, there's a inherent hazard level matrix that operates on different soil types. So depending on the regolith and the erosivity, so the rainfall zone you're in, there are certainly differences in terms of the likelihood for water pollution. And I suppose outside of the roading network that I've talked about here, there are implications for filter strip widths and things like that in riparian zones. So there is some influence, but not necessarily on the things I've just talked about in this talk.
Thanks, Ashley. So I'd just like to thank Ashley again for presenting for this month, and thank you all for attending, and see you next month.
Thanks, Abby. Have a good day, everyone.